do worse if your compliance goes down. So the point here was to show that now that we have enough data, these types of policies give us a sense of how you can deal with situations in which a portion of the users can be incentivized. And we're really at a time where just the value of information already provides way for people to change their behavior. TomTom was very successful in creating a 7-hour gridlock by sending everybody to the same spot. So that means if you send people information, they will certainly react to it. And the work we're doing now focuses on the way we should try to do this, either by information sharing or incentivization. So going back to expansion and what we're doing now, I think where we're going with this is, first, massive data fusion. In our system today, we've used data that comes from satellites, the German DLR. Even at some point, we programmed the satellite to orbit around California so we could gather data. From UAVs, that is, we obtained through the Air Force, and then of course all the sources of data that I mentioned before. And the point here is that, one single, we love the phones, but the point is the phones by themselves just won't do it. So data fusion is something which works at global scale only if you integrate all these different sources of data. And the things we do with this, and that's in collaboration with the School of Public Health, is how to use this to predict hour-by-hour noise levels in cities. Right now, noise levels are predicted at the graduality of 1 year based on traffic counts. But with these models and understanding speeds and all these other quantities we can measure, we can build this into noise models. Other things we're doing with Ron Cohen and Edmund Seno is use this to characterize emissions, and this is the result of a very simple dispersion model that Edmund put together, the Caline model. It's not going to be 5 years before phones have air quality sensors. It will happen ultimately, and the prototypes are in development. But until that's the case, you can really rely on traffic monitoring to at least infer what emissions would be, and these are things that we're working on. I think the big opportunity for data is data procurement. After the explosion of smartphones, a lot of the federal and state, well, the federal DOT, but certainly the state's DOT, have shown enormous interest in buying data, but they don't know how to buy data. So one of the things that we had to do is to write a procurement procedure for the state of California in which we define the acquisition procedure and the data quality standards. And we are far from understanding how these things work well. I mean, you buy the data by the volume, you buy data by accuracy, how do you define quality, and so on. And so it's just at its infancy, but this is probably going to explode also because the secondary network is just not a small enough place that it can be instrumented. So data from the private sector has to be bought, and there's a lot of challenges with that data. So this is the volume of data that we get from a given provider, and it changes radically from the day to the night. But the point is, you don't really care day or night. You care to have data when there's a traffic jam. And the latency, if you give me a GPS point which is 5 minutes old, I can't make any use of it because it's obsolete. So all these metrics are things which are important to take into consideration when doing procurement. The next big thing that is going to happen with this in California is integrated corridor management, ICM. And I think we come from a world where we've been used to instrumenting infrastructure quite well. California has a fairly well-instrumented freeway system with ramp meters, with changeable message signs, with HOV and HOTs, just like in the work which was done here at Georgia Tech on HOT, HOV lanes. And the thing that the Department of Transportation is really interested in investigating with us is, well, if the freeway is already centered anyway, the only thing you can do, especially in LA, is to start diverting some flow. And if you were even more fanatical, to actually divert people into the transit system, or bikes, like Carrie is doing. For this, you really need to convey that information to people. And so this notion of rerouting a portion of traffic, like I was indicating before, on this very theoretical and preliminary stage, is something we will implement within 2 or 3 years. And there's no way we can ever model people at the individual level, but understanding in the aggregate what should be done so an optimal can be reached is something which is fairly important. And what that means institutionally is that it's really an institutional nightmare. You have to deal with NPOs and state agencies and federal agencies, and you have to make them communicate with transit agencies, and you have to use sensing infrastructure, which is shared between the private and the public sector, have industry partners from which you can do data procurement, and potentially run your app yourself, like Carrie's running her own app for her own lab. So that's what we're doing now, and that's fairly challenging. The state of California has given us the mandate to take over 1 freeway in Los Angeles. everything seems to indicate that 710 is a very good candidate. We hope to be able to start to take over its infrastructure within the next couple of months. And so, you know, if you think about what it takes to take over that infrastructure, that means you're creating an entire decision support system. And the part I've talked about today is basically the yellow box. The first 15 minutes of the talk, Mobile Millennium, that's the yellow box. That's data coming in and information spilling out. So in a sense, in the last 4 years, we built that yellow box. And in the next 3 years, we have to build the rest. So there's a lot of work. We're recruiting a lot of people, and we're very excited about it. But the point is that doing this is quite challenging. I mean, you have to do forecast, you have to do control, you have to do human in the loop, because there's no way they're going to let a Berkeley run algorithm control the fluid automatically. You've probably all seen the movie The Italian Job, where a hacker takes over the District 7. Well, this is not happening. We have to keep humans in the loop. So the next challenge is, and this is by no means a way to show this is where ITS is going, but these are some of the very exciting avenues which are going to be game-changing in ITS in the next couple of years. And again, this is very biased because these are the things I'm interested in. There's probably another 5 graphs like this you could do. But certainly if you think about what's changing today, distributed and control estimation has traditionally and will play a very significant role in transportation. That's not changing anytime soon. Behavioral economics, like lotteries like they do at Stanford with biology, Prabhakara's group, or eco-driving, this is changing. This is really already disruptive to the field. Social networks is huge, especially with companies like Waze. Procurement and policy is also going to be disrupted with this private sector data. In the next 18 months, you'll have connected vehicles which really start to grow up. I mean, the Android Galaxy S3 has already been sold in 30 million copies in the world, and this is one of the first phones which has full IVI integration with the Mirrorlink protocol, and that's just the beginning. That means your car can now play all your apps if you use that phone. I'm not working for Samsung, I'm not doing commercial. They're not funding our work, by the way. But the point is to showing that things are changing, and in 18 months there's going to be a revolution, and that means insurance will be very, very abruptly disrupted. Today, to get an insurance premium, you have to disclose your income level, your credit score, things which are completely irrelevant to your driving. Okay? But tomorrow, and in fact this is happening today with companies like Metromile and so on, you can monitor people and assess the risk based on the data. That's going to be revolutionized. Of course, autonomous driving is what everybody's thinking about, but that's not happening before the next 5 or 10 years. It will completely be game changer, and mobility on demand work from MIT is key there. But this is a longer time horizon. So the pink things are the things I'm interested in, and maybe in the last 2-3 minutes, I'll just show a couple things on it. For example, we work with Waze, which is the biggest social network for transport, and we're trying to correlate traffic to postings, and these are the polite postings on traffic, and then we filtered out all the politically incorrect things people post when they disclose their traffic, but you can, and this is where I live, so you can see all what people post when they drive around where I live on Waze, and this provides very interesting information. Other things I'm interested in is, like, I'm advising a couple of startups. One of them is going to provide services in which insurance premiums are actually tailored to your driving. If you're a good driver, there's no reason why you should pay more than a bad driver. And so this StreetOwl Refuel Me app enables to do that, and that's one of the game changers. Another company which is relying on the Mirrorlink protocol is completely diving into the car infrastructure. And again, in 5 years, every phone app will probably be able to be played in most of the major car IVI systems through the Mirrorlink protocol. And so today what we see is a lot of companies interested in building tablets. This is one we built in China, and we're trying to see how it can be commercialized. That is completely compatible, so you can either put this in your car or use it as a tablet, and basically all your apps can roll through that system in your car. That's going to be completely game-changing in terms of how data is collected and people interact with their commute. So what are we going to do in the future? We're also working on smart buildings. This is a completely different app where we're trying to monitor efficiency of buildings, and in particular characterizing how people interact with their environment, how much data, how much energy they're consuming. That particular app is basically what we call Energy Eyes. You can scan any device, and with its QR code, it's going to figure out how much energy it's consuming based on sensors we'll also deploy. So here it's like energy disaggregation using these sensing. So the algorithms are very similar to what I showed before, except it's working for buildings, and that's something we're implementing in Singapore. One of the Berkeley has an entire floor that we're instrumented and we're working on. Another thing we did in the past, which was another smartphone thing, is trying to use smartphones to create shape maps. And here the idea is that an accelerometer might have enough accuracy to, if positioned properly, monitor an earthquake. And so we did a lot of early testing of how to use these vast amounts of smartphones to monitor earthquakes. These are shake tables we have at Berkeley, and basically they reproduce earthquakes that have been recorded in the past. So it's not like in Star Trek where you move the camera to look like you're in outer space. This thing is actually shaking for real. And what we were trying to figure out is, how good the signal is and how that can be used. Maybe the last thing I can talk about, so you've seen driving phones, you've seen shaking phones, you've seen energy phones. I want to show you what a swimming phone is. So I brought a little toy here. You can pass it in my last slide. This is one of our 100 floating robots. They're powered by phone as well. And here what we do is, just like for traffic, when we launched Mobile Millennium, we were among the first people to see how to integrate mobile measurements in flow models for traffic. Well, we're doing this also with water. This is the what these things look like when they're in the water. This was in the Berkeley swimming pool. So all of these can measure local currents, and they gather the positions on GPS using GPS, and then they can even dive and measure things below the water. The Air Force even wants to pull them from helicopters, so we've tested bring them from bridges, and people really didn't like it because it was dangerous on the boat traffic. But here the point is, like, you can collaboratively map things underwater. In fact, we're talking with Google on how to use this for Street View underwater. As you know, Google was interested in doing that. And so we do a bunch of deployment of these in the Sacramento Delta. And the thing which is interesting is that watching traffic and watching water currents is boring, so you have to accelerate all this. It's not fun. But the type of things we do here is, when you navigate in water, you actually have to avoid obstacles. It's quite difficult. So what you will see soon in the video is at some point, these things will start moving as states. And what's very difficult here is the motion in unstructured environments, because you're completely uncontrolled. You don't even know the current's accuracy. You have at best a shallow water model. And so you can probably see, this guy now starting to move, and you'll see another one moving pretty quickly. And so how to collaboratively reconstruct the currents and map them, you can see now it's adjusting itself, it's adjusting its position to kind of not go into an obstacle. So same algorithm, same philosophy. I think it's been a very exciting time for civil engineering. I think that civil engineering is undergoing a set of revolutions. I think traffic was the first one. I think computing and infrastructure is definitely going to be the next one. Moving sensing has tremendously changed the field. And so I think that in the future, building these infrastructure systems, instrumenting them, and creating the proper policies to operate them is going to be at the key of what we do in water, in traffic, in energy. And I think civil engineers and engineers in general, but civil engineers have a really important role to play in that equation, because we are the ones who build the infrastructure in the first place. So we should be able to operate it better. I want to thank all the PhD students who have worked on this, and also we have a fairly extensive staff of people, in particular software engineers. And the thing which is important is it's actually very hard to build these systems if you don't have professional staff. And so working in that context has been extremely beneficial, and I think provided a very rich environment. So it's been a pleasure to work with all these people. I think I almost exceeded my quota of time, but we're 1 minute over. I don't know how much time I think here, but thank you very much again. It was really fun to I can take whatever is allowed by the time.
I don't see anyone banging on the door yet, so does anyone want to be helped?
Yeah. It's very good. It's a quick question. It's already mentioned about the Challenger 2, about GPS expansion. I was going to learn a little bit. I think in the past there's a lot in that area that's down. So what's the difference in terms of the Challenger there compared with
the challenge was for us, we did not know how to deal with map matching and mapping first with low sampling frequency. And I think now